Welcome. Today I would be talking again to the lecture number 5. Some points I will clarify regarding the phase behavior of mixture. In this I shall be specifically looking into the phase change behavior of a binary mixture. So first we shall look into how the phase changes for condensation, and in this, as I told you earlier, that we can represent this in terms of the temperature versus composition at a given pressure, or pressure versus composition at a given temperature. So let us see the difference between the two. So first I take up the temperature versus composition diagram and for a binary mixture, and you can see that the x-axis represents the mole fraction of the less volatile component, whereas the y-axis represents the temperature, and this is at a constant pressure. And this kind of diagram we have seen earlier. In this particular diagram, this top curve represents the dew point curve, whereas the bottom curve represents the bubble point curve. And here we have seen that there are many tie lines which are joining the phase compositions at equilibrium. Now let us consider how the phase changes when we start from a vapor state. Like the point 1 represents the vapor state at some temperature, and this is above the dew point curve. So this is at a superheated vapor state. Now as we lower the temperature at a given overall composition, this is the, if you come straight down, the overall composition remains the same. So as we are cooling the vapor down, we find that up to certain temperature it remains in the vapor state. Then at some point 2G and at corresponding some temperature, that is the temperature we call the dew point temperature. So at this dew point temperature, the liquid phase starts forming from the vapor phase. And what happens after that? As we still lower the temperature, we get more and more of the liquid, and we find that at every stage, if we carry out the process very slowly, then we may assume that at each temperature the two phases, that is vapor and the liquid, are coming to equilibrium, and then we can make these tie lines like 3G 3F to figure out the compositions in the liquid and vapor phases. Okay. So now in this particular region we are having two phases, and as we still lower the temperature at certain temperature, that is represented by 4F, and that is the bubble point temperature, what we find, the last amount of the vapor has gone into the liquid phase. And after that, if we still lower the temperature, we go into the subcooled liquid region. Now in this case what we find, the 2G, which is the dew point temperature, here we have the saturated vapor, whereas at 4F, which is the bubble point temperature, this is we have the saturated liquid. And understand this, that this 2G and 4F, these two temperatures are dependent on the pressure for the given composition. That means at the same composition, if I change the pressure, I will get a separate set of dew point and bubble point temperatures. Okay. Now let us go to the next way of changing the phase, and now in that we shall be looking into how the phase changes for the change in the pressure at a given temperature. Now in this case what we are doing, again we are plotting this particular x-axis is representing the mole fraction of the less volatile component, and whereas the y-axis is representing the pressure. Now how to identify that whether it is more volatile or less volatile? This I just recapitulate, that because we are talking of the binary mixture, so that means mole fraction of some component A will be enough to describe the composition of the system, because the other mole fraction will be 1 minus this particular mole fraction. Okay. Now because now we see that at the two extremes, that is at x equal to 0 and x equal to 1, at these two extremes we have the pure components. That means x equal to 0, x a equal to 0 means there is no a. That means there is only other component B, and for that particular component, this is the vapor pressure. And at XA equal to 1, that is, it is pure A, we have the vapor pressure of component A. Now, because the vapor pressure is more for component A, we can say that the A is more volatile. Okay. So, this A is more volatile. Oh, I said that it is less volatile initially. Sorry, this correction, that this A is more volatile component, whereas the other component, this B, is the less volatile component. And please contrast it with the previous one. Here you can see that in this case, we find that these two extremes are representing the boiling points at the given pressure, and whichever has the more boiling point is less volatile. Okay. So, the less the volatility, the more the boiling point, the less the volatility, the less the vapor pressure. So, that is how we distinguish between this pressure representation and the temperature representation. Now, you can see here that we know that if you increase the pressure, a vapor will go into the liquid phase. So, to get the vapor, we need to have low pressure. Now, in this case, as I explained in my earlier lecture, that here also we get these two curves, but in this case the dew point curve is at the bottom, whereas the bubble point curve is at the top. Okay. Now, you see that suppose this particular point R represents the superheated vapor because it is below the dew point curve. So, this is superheated vapor, and for superheated vapor, if I want to get liquid out of that, I have to compress it, that is, I have to increase the pressure. Now, as I increase the pressure, what happens? Up to certain extent, it is remaining in vapor state, and at certain point S, at this point we find the first drop of liquid is formed. Now, at this point, whatever pressure we are reading, that is the dew point pressure. Now, if we still increase the pressure beyond this dew point pressure, we find the two phases are formed, and for example, here also we will find that in the two phase region I can have tie lines, and that means if we are increasing the pressure very slowly, then we may assume that at each pressure there will be equilibrium between the liquid and the vapor phases, so that we can use a tie line to correlate the liquid phase and vapor phase compositions. And as we still go on increasing the pressure, at certain pressure U, that is the bubble point pressure, we find that last amount of vapor has gone into the liquid state. That means, if we still increase the pressure beyond the point U, that is the bubble point pressure, we find we have now the compressed liquid. Now, please understand, compressed liquid and subcooled liquid mean the same thing, they represent the same state. Only thing is this, the names are different because the compressed liquid means that we are getting the liquid by compressing a vapor, whereas subcooled liquid means we are getting the liquid by cooling a vapor. So, these two processes are different to obtain the liquid, even though the state are one and the same. So, subcooled liquid and the compressed liquid mean the same thing. Okay. So, in this we find that here we are getting the compressed liquid and that is represented by say point W here, and similar thing will happen if we start from point W, that is liquid state, and keep lowering the pressure. First we will approach the bubble point pressure, and still further lowering we shall be going to the dew point pressure, and ultimately we shall be going into the superheated vapor region. Thank you.